And now up is Lisa. Lisa's going to talk to us about PERUN. This is really exciting about virtual channels and routing. So good luck.
Thanks. So hi, I'm Lisa. I'm going to present to you PERUN. And I want to start, and this is a joint work from the University of Warsaw and TU Darmstadt. So I want to start by giving a very high-level overview of what we actually try to do. So we are in this setting where we want to have payment networks. So we've talked about this quite a lot, so I'm going to skip the basics and just say that we want to have a connection between Alice and Bob here. So Alice and Bob want to do micropayments, really fast, really cheap, for very small amounts. So that's important to them. But they don't want to open a new channel on the blockchain because that is expensive. So what they want to do instead is they want to use existing channels that they have with some intermediary. In PERUN, we always call the intermediary Ingrid. So we already have seen quite some channel network constructions, and many of them are based on the hashed time lock contract. The idea is that when Bob wants to receive a payment, he thinks of a random number X, hashes it, sends the hash to Alice. Now Alice creates a hashed time lock contract with Ingrid, which includes this hash and a timeout, and Ingrid does the same with Bob. I'm saying here that the timeout has to be smaller, but as we've seen before, it might actually not have to be smaller, but anyways, these two connections have to be established. As soon as Bob wants to receive the payment, he has to reveal X. So he sends X to Ingrid, who then has to pay to Bob. And Ingrid will take this information X and also publish it on her side to Alice, so she will be secure to get her money back from Alice. That's a very clever approach, and we've seen it out there already. But the downside of this is there's actually quite a lot of things going on for a single payment. And as I said before, we want to have micropayments, so really fast, really cheap. And the problem here is that we need 5 messages at least. Many times we actually need much more messages to execute a single payment routing here. The availability of Ingrid is also a big question here, because if Ingrid is not very fast in responding, this delays the whole process. There's another question, maybe for every payment we have to find a new route, so that takes us additional time. And of course, Ingrid wants to be paid for her service. So she wants a transaction fee for every transaction that she routes in this network. It's probably going to be much cheaper than routing it or sending it directly over the blockchain, but still. And there's additional problem that we also have heard today, or yesterday before, that Ingrid has a lot of control over this channel. She can see everything that's going on. She knows all the intermediate messages between Alice and Bob. And if she doesn't like what's going on, she could also refuse to forward this message. So she has a certain amount of control over what's going on here. So we want to get rid of that. Instead, we want that Alice can send over this construction a direct message, a direct payment to Bob. And that's what we need to get micropayments. We want that they can also send it back, so really fast, really, really cheap payments here. And they don't go over Ingrid at all, so she doesn't know anything what's going on. We have privacy towards Ingrid in the same way that a basic direct channel over the blockchain gives us privacy towards third-party users. Ingrid might know the end balance of this communication, but she doesn't see every single transaction. And on the other hand, we can achieve a very high throughput here, because the speed of how fast they can send these transactions is only based on how well they are connected. We could even think of complete internet-free connection. They could talk near-field communication. It doesn't matter. They don't have to route anything over the internet if they don't want to. So this can be really, really fast, pretty much the same as in on-chain channels. So that's what PERUN is building. And on top of that, we are very interested in provable security of all the protocols that we built. The main key aspect that we want to prove is that the payments we send in channels and networks are just as secure as a payment that we send directly over the blockchain, like a direct blockchain transaction. So how do we actually show this? Well, we've seen very often that when protocols are designed, sometimes there exist mistakes. And then there are clever people out there that find attacks on this. And from these attacks, the protocol designers learn, make it better, and there's new attacks. This happened all over the place. We have seen this in TLS and many other protocols out there. This is called the cat and mouse game of IT security, and I'm pretty sure you've heard about this. So how do we get out of this spiral here? Well, one way that modern cryptography is aiming to solve this is to build security proof, security from the beginning. When we design a protocol, we already show what kind of security we achieve with this, even if we don't know all the attacks out there yet. And the approach that it's doing is first we define formally what does it actually mean, security? What do we want exactly? And then we construct the protocol, all its messages, maybe smart contracts inside, and so on. And in the end, we sit down and prove that this protocol actually achieves all of these formal security definitions that we have made in the beginning. Okay, so that's a very high-level introduction to what I'm going to talk about today. And in detail, I'm first going to start talking about how we built the basic channel, the ledger payment channel, so directly a channel with a blockchain underneath, and how from that we go to the virtual channels, so extend it to a payment network. Then talk a little bit more about the provable security model that we are using and summarize. So what do we need to build PERUN? Well, we need a stateful cryptocurrency like Ethereum that supports smart contracts where we compare two digital signatures. Because our model is similar to the one that Patrick was mentioning earlier, we compare versions or counters. So we need a cryptocurrency that allows us to compare two versions with signatures to determine the right one. So how do we open such a ledger channel? Well, we have Alice and Bob here, and they want to open a channel over the blockchain. What they do is they have a smart contract up here. The smart contract stores their information about their addresses and, of course, the coins. So this is what we are going to use to represent such a basic ledger channel. It has the identifier beta for basic ledger channel, has a version 0, and it has some coins blocked, XA coins for Alice, XB coins for Bob. So now we update it. Alice wants to send 1 coin to Bob. What she does is she creates a new version of this balance distribution. So beta 1 is now 1 coin less for Alice and 1 coin more for Bob. And in order to make the payment, she signs this and sends a signature to Bob. That's a single transaction, a single message. That's very clean, very easy, potentially very fast. So Bob now has all of the information to ensure this balance distribution. So he gets the coin that Alice sent him. So now when they want to close, Alice will maybe try to close an outdated state or only has an outdated state. So she puts beta 0 in the smart contract. The contract then, of course, has to wait for a couple of rounds, so Bob has the opportunity to see, oh, wait, something is going on, I need to react. And then Bob sends the information he got from Alice, the new distribution of coins, and, of course, her signature to make sure that the contract, or to prove to the contract that Alice agreed to this new distribution. And the contract validates both of them, sees, oh, the version of Bob is newer, so Bob's statement is correct, and the coins are paid out accordingly. So that's a very simple representation of how a channel works. So now we want to extend it. So imagine we have a network like this. We have Ingrid in the middle, and she has a lot of connections, a lot of channels to other users. This is what we call a hub. So now we want to connect all of these users. So let's see how to open such a virtual connection. We have 2 basic payment channels here, ledger channels, each of them supported by a smart contract that is on the blockchain. We don't need them right now, but still they're there. And now, in order to open such a virtual connection, Alice and Bob send their opening statement, an opening certificate to Ingrid. If Ingrid receives both of them, so the statement I want to open, this channel gamma 0 with XA and XB coins inside, and it has a predefined validity in this case, and it receives both signatures from Alice and Bob on top of this. Then she says, okay, great, so you seem to be okay with this. Let's update the 2 ledger channels and block the coins for this. So in each channel, we block XA coins on the left side and XB coins on the right side. So now these coins are blocked for the predefined validity down here. The validity is a simplification that we use in this case to show that, well, Ingrid has to have the guarantee that at some point she gets the money back, right? She doesn't want this to be open forever. So for now, let's just say it's a predefined validity, but you could always extend the protocol to have this flexible. Okay, great, now the channel is open, now we don't need Ingrid anymore. And now the update is identical to what we've seen in the update of the ledger channel. Alice just takes her signature on a new distribution of coins, send it to Bob, one message, really fast. And there we have micropayments. There we can really have a lot of payments in a very short time in two directions. Okay, good, but now comes the tricky part, how to close this. Well, okay, let's start with the easy tricky part, so everyone agrees. That's always the nice part. Alice and Bob send the latest version, both signatures, everyone agrees, great. Ingrid sees both of them, says, okay, great, let's update. And then they update the underlying ledger channels back to a version where this one coin goes from Alice to Ingrid and from Ingrid to Bob. Now the virtual channel is closed. But of course, well, it's not, we have to also consider the hard part. When, for example, Alice aborts or disagrees. So now Bob wants to close the channel. So Bob is here, sending the latest state, the latest distribution of coins in the channel. And to prove that he actually didn't invent it, he sends Alice's and his own signature to Ingrid. Okay, now Ingrid is trying to reach Alice, but Alice is gone. So Ingrid needs to make sure that she gets the money. So what she does is she closes the underlying ledger channel. So the ledger channel that was here before is just closed in a procedure as we've seen in the beginning of this talk. But on top of the normal closing procedure, she adds two witnesses here. The first witness needs to prove that, in fact, there was an open channel, an open virtual channel between Alice and Bob. And to prove that Alice agreed with it, she has to append the opening certificate that she got in the beginning from Alice. And then on top of that, she also wants to get the latest distribution of the virtual channel. So the second witness is the one that she got from Bob just earlier. And it is the latest distribution and Alice's and Bob's signature. Okay, good. Now the smart contract has to wait for T rounds because Alice might have to say something about this. Maybe Ingrid is trying to cheat and Alice must have the opportunity to react to this. So after time T, it actually can start validating. So maybe Alice responded, maybe she didn't, but since Ingrid had the correct version, we know that this version will win. But one thing the smart contract has to make sure is that the validity of the underlying channel is actually over. Because this channel should not be closed while Alice and Bob are still active inside. So if this check does not pass, the channel won't close. And it only will close as soon as the validity has passed. But if it has passed, it will just evaluate the states and pay out the coins accordingly. So Ingrid gets her one coin here, and now she's ensured, okay, great, Bob still is honest, these two parties still agree, so they will simply update the ledger channel that's underlying here. And this part never goes to the blockchain. And this one coin goes from Alice to Ingrid, from Ingrid to Bob. Okay, so now, oh yeah, right, very important. Ingrid must never lose coins, right? But we have that in any channel systems. So let's compare some of them. Let's compare the direct channel that we have on the ledger. We call it the ledger channel, so a two-party connection, no intermediaries. The hash time lock contract construction, where we route every single transaction over intermediaries, and the PERUN network construction. So the networks are always better because we don't have to go to the blockchain to open and close. That saves us a lot of fees. So whenever we can, we should probably use the network solution. But then we still need to pay the intermediaries for their work. So we need to pay fees for their service. So in the hash time lock contract, we pay for every transaction that we want to be routed a fee. In the PERUN network, we pay once a fee for a predefined validity, and then within this time, we can send as many transactions as we want. So the fee model is different. And I'm not saying PERUN is always better. I'm saying that there's actually quite some applications where you should think about which one makes more sense. And micropayments, if they want to be really fast and really cheap, then probably this is the cheaper model. Another advantage that PERUN has over the hash time lock contracts is that it gives you the same amount of control over the channel as the direct channel does. So the intermediary doesn't surveil, cannot see what's going on except for the end balance, and it cannot control. So it cannot censor transactions. And as I said before, micropayments are really nice in ledger channels and really nice in a PERUN network, and not quite so easy in hash time lock contract-based networks. Okay, but I promised to also talk about the security. So we tried to formulate 3 security properties that we need of the channel network system. We want, first of all, that the intermediary always stays financially neutral, balanced neutrality. So it must not lose coins as long as it's honest. The second one is that the end users will always be guaranteed to get their money within some predefined timeout. The money cannot be blocked. They always know when they will get their money back. And as soon as I get a transaction, a message saying, I gave you 1 coin, I know I can get this coin. So I always have guaranteed payout. And the last important property is that we need consensus on updates and creations of new channels. It would be very bad if we have a channel and then one of us is convinced that it actually is opened and the other one thinks it's closed, because this would lead to serious problems. So the last property is consensus on updates and creation. And all of these properties must hold even if everyone else in the system colludes. So this must hold even if there's one single honest party and everyone else is Byzantine. So how do you prove this formally? I don't want to show you the proof in detail because A, that would be way too much to do right now, and B, I think most of you are not that interested in how we actually do it. So I will give you a very high-level idea of what model we use. And this is a model that you've heard over the last 2 days from time to time. It's called the universal composability model. And the key idea is that we have this complicated protocol that involves multiple parties, a smart contract, lots of messages, timeouts, signatures, crypto. So there's potentially a very complicated protocol. And what we do in order to define and analyze its security is we create an ideal functionality. And this ideal functionality has the same input-output behavior as the real world, but otherwise it's very simple, very clean, and gives you just the key idea of what it's supposed to do. So in the channel case, this could be something like a completely trusted third party, something that is definitely only doing what we tell it to do, and there's no, and it's completely trusted, and it would just take in the beginning our coins. Whenever we want to update, we give it a message saying, here, send 1 coin to Bob. It would internally write down the current balance. And when one of us says, OK, close, it would give us the correct amount of money back. So there's no disputes. There's very simple update procedure. So now the last step of the actual proof here is then to actually show that these two are identical, so that the input and output behavior is identical. And that must hold especially when we consider attacks. So for every possible attack that we could have in the real world, someone aborts, someone misbehaves, someone sends wrong messages or not in time, the same attack must also be possible in the ideal world. And that's important because if we turn the statement around, what it means is that if the ideal world is secure against some attack, then our protocol is too. So the ideal world shows us, if we want to see if it's potentially attackable by some attack, we just look at the ideal world and we can say yes or no. And that's actually really neat because the UC model is quite nice in 2 properties. The first one is we can abstract a very complicated protocol into a very simple smart, black box behavior. And then the composition theorem of the UC model says that this black box we can use and put it in a very complicated protocol and reuse it a lot. We can run it in parallel. We can run it in concurrent settings. The same user can do it multiple times with the same other user. And still, we achieve security. And this is a very nice property that most of the security frameworks out there don't give us, but this one does. So, yay, you see. OK, so now let me quickly summarize what I've told you today. We've seen a new formalism of what it means to have state channels and networks, especially the virtual payment channels, so channels that are opened and closed over an intermediary, where we don't go to the blockchain, but we go to the intermediary. And this is nice because the intermediary can't interfere with that channel, and we have a very nice fee concept here. And on top of that, we've proven our protocol to be secure in the UC model. But of course, we've thought of quite a lot of extensions. We are working in Ethereum, so it would be very nice if we could have also state channels, not just payment channels. And we also want to have larger networks, not just this hub network with one central party in the middle. Of course, that is efficient, but, well, we want to have broader networks, longer channels. So these extensions are actually quite interesting, and my colleague Christina will tell you more about these extensions after the lunch break. Okay, so thank you very much.
Awesome. So what was the typo?
Huh?
What was the typo?
Really important.
No, it wasn't.
Life or death. Okay, so we have time for one or two questions. I'll jump to Pedro first. He was like skyrocketing. He literally touched the moon. Yeah. There you go. Okay,
hello, really nice talk, thank you. So maybe you mentioned, but I didn't get exactly. So imagine that there is Ingrid and there are several Alice and several Bobs. How's the collateral of Alice actually handled? Does she need to log coins for each pair of Alice and Bobs, or can she share that value?
So if we look just in the channel between Alice and Ingrid, there might be multiple virtual channels on top. One with Bob, one with Charlie, one with Dave. So for each of them, she needs to open a new virtual channel inside. And for each of them, she needs to block coins. So the channel Alice-Ingrid, of course, there's like money on the blockchain is only blocked once, but inside the channel, she needs to block for every parallel virtual channel. If I have first a channel with Bob and then with Charlie, of course, I can reuse the money.
Thanks for the talk. My question is, have you tried to implement similar approach in Bitcoin, for example, and what kind of functionality did it miss to create such virtual channels? Because, well, I don't see where you use like infinite loops or something like that. Mm-hmm. And though Bitcoin can compare integers and so on, is it possible to implement it in Bitcoin?
Okay, so we haven't analyzed that. So far, I've always thought that we need stateful blockchains because we need to compare to states, right? There could be a dispute. One says this channel was open, the other one says, no, actually, it's already closed again. So these things that we need to compare get much larger than they are in the channel networks that we have seen so far. But with the replace by counter, I'm actually not sure. So it would be maybe interesting to look into that.
There's a question here.
I have a question about economic incentives, for example. So if you want to do only one transfer between Alice and Bob, maybe it makes sense to not necessarily have a virtual payment channel. If you want to do 200 transfers, maybe it makes sense to actually have an on-chain payment channel. So my question is, what are kind of the limits that would fit, what use cases fit this solution better?
Okay, so of course this strongly depends on the fees that the intermediaries take for their service, and also on how long they take it on average. So if I have a Lightning channel, it would be very interesting how long this collateral of the intermediary is actually blocked. If by average it's blocked for a minute, then, and I want to have transactions per second, then this might make sense. If the intermediary is actually highly available and can react really, really fast, and also do this very cheap, then it's probably for very few transactions easier to just route them. But my assumption is that there might be a highly available intermediary might actually be more expensive than an intermediate that only goes online occasionally. So you could use this cheaper intermediary and run PERUN on top of it to maybe save some costs.
Awesome. And is there any questions down this side? Yes, there was. Of Terrace again. There you go.
So I have a question about this slide that was talking about the comparison, and so why micropayments are not good for HTLCs and are good with PERUN? I didn't really understand.
So the idea is that you need a lot of messages to send a single transaction in other networks. For example, in Raiden, you showed the slide where in order to send one payment, you iterate a lot of messages in one direction, then back, then forward, then back, and so on.
But these messages are always off-chain, so...
Always off-chain, but still. I'm just saying that this might take you seconds, and you might not want to have seconds.
I would argue it's more in the millisecond.
Well, then it might be quite interesting to see where the point is, where what system makes more sense.
And another thing, you also mentioned that they're controlled by an intermediary in an HTLC. So what kind of control did you mean?
So when I want to send 5 transactions, and after the 3rd transaction, the intermediary says, oh, wait, actually I don't like this. I don't want you to send so many transactions to him. I could just stop communicating with you or stop saying, okay, I don't want to route this anymore. And this is something the intermediary doesn't even see in PERUN. So he cannot even see how many transactions you've sent. If he opened it, he has to agree with it.
Okay, and then another final one. Sorry for the many questions. So did I understand correctly that essentially there has to be capital locked, extra capital for the virtual channel on top of the normal channel?
Yes, but so this is something that also happens in hash time lock contracts, but only for the time that this one transaction is routed, and then it's free again. In our system, it's locked for the time that the channel is open. So I would assume that the virtual channels, most of the time, will only be open for a small time, not for days.
Okay, because I was thinking about the liquidity that it would affect the network and make it more difficult to route the normal HTLC payments if there were PERUN channels on top. But that's why I can see why hubs are important use case where we could have virtual channels on hubs.
Yeah, so we used hubs also to simplify the security analysis a lot, but Christina will actually show how we can extend this model really nicely to longer channels.
Great, looking forward to it.
Awesome. Okay. A round of applause for Lisa again. Yep, Lisa, yep, that was awesome. Thank you.